Tonight, we begin with a problem that should not have existed. In 1933, the astronomer Fritz Zwicky was studying the Coma Cluster, a vast gathering of galaxies suspended in the dark, when he noticed something deeply unsettling. The galaxies were moving too quickly. If the cluster contained only the matter astronomers could actually see, then by every ordinary expectation, it should not have remained bound together at all. Something else seemed to be there, something unseen, adding weight to the cosmos without adding light. Picture the quiet strangeness of that moment. A scientist looks into the heavens and discovers not simply a new object, but evidence that the universe may be built upon structures hidden from sight. What made that realization so powerful was that it was not entirely new. Long before dark matter entered the language of modern cosmology, science had already been circling the same unsettling possibility. Newton could describe gravity with extraordinary precision, yet he could not fully explain how one body seemed to influence another across empty space. Faraday imagined invisible lines of force stretching through the world around him. Maxwell gave those forces mathematical form and showed that light itself belonged to an unseen field. Then Einstein transformed the picture again, suggesting that space and time were not passive emptiness, but part of the physical structure of reality itself. This documentary is about that long intellectual transformation. It is about the moments when scientists began to suspect that the universe was not defined only by what could be touched, weighed, or directly seen, but also by fields, curvatures, hidden mass, and faint cosmic traces that could only be inferred through their effects. Again and again, human beings were forced to follow patterns before they could claim understanding, and to trust consequences before they could name causes. If you imagine yourself standing in an early observatory or listening to the hum of sensitive instruments in a 20th century laboratory, you can almost feel the same tension that accompanied these discoveries. The answers were not arriving as obvious objects. They were arriving as disturbances, mismatches, and quiet signs that reality was deeper than appearance. So tonight, as we move through observatories, laboratories, equations, and moments of profound uncertainty, we are following a question that changed science forever. What does it mean to discover something that remains fundamentally invisible? And how much of the universe is shaped, even now, by realities we know only through the marks they leave behind? In 1933, the Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a vast congregation of galaxies hanging in the darkness far beyond the Milky Way, when he arrived at a conclusion that did not sit easily with the visible universe. The galaxies inside the cluster were moving too quickly. If their motion were governed only by the matter astronomers could actually see through their telescopes, then the cluster should not have remained intact. It should have loosened and scattered, its galaxies drifting apart into the black. Yet Coma held together. Gravity, somehow, was doing more work than the light of the galaxies seemed to justify. Zwicky proposed that there must be additional matter there, matter that did not shine, matter that announced itself only through its pull. It was an unsettling thought, and not only because it hinted at missing mass. It suggested that the universe might be organized by structures that did not reveal themselves directly to the eye, but only through their consequences. That kind of realization has a particular stillness to it. It is not the drama of a new continent suddenly appearing on a map, nor the thrill of spotting a bright new object where none had been seen before. It is quieter than that, and in some ways more disturbing. A scientist measures what seems to be a perfectly ordinary system, and the numbers refuse to agree with appearances. The visible world ceases to be enough. In moments like that, science does not move forward by seeing more of the same. It moves forward by accepting that reality may be structured by something hidden, something that cannot yet be pictured clearly, something that must be inferred from pressure, motion, distortion, or imbalance. That method, the patient reading of traces, has become one of the deepest habits of modern science. It is also one of the strangest. Human beings evolved to trust what can be touched, heard, weighed, and seen. Yet some of the most important discoveries in the history of physics began when observation forced the mind beyond the comfortable limits of the senses. If you linger for a moment inside that tension, the subject of this documentary begins to take shape. The invisible structures that shape the universe are not all of one kind. Some are forces, some are fields, some are geometries, some are hidden forms of matter. Some may be properties of empty space itself. They do not belong to a single century or a single discipline. Rather, they form a long thread through the history of ideas, tying together the work of natural philosophers, experimentalists, mathematicians, astronomers, and instrument builders again and again. The surface of the world has turned out to be thinner than it first appeared. Beneath it, or within it, or woven through it, there have been deeper arrangements that only slowly emerged into human understanding. One reason this story matters is that it is not merely a history of discoveries. It is a history of changing standards for what counts as real in ordinary life. Reality seems simple enough. A stone falls. A magnet pulls. A beam of sunlight warms a wall. A planet moves across the sky. But once science began asking not only what happens, but why it happens, the old confidence began to erode. Is a force real if no one can see the mechanism that carries it? Is empty space truly empty if something in that emptiness can transmit light, organize matter, or bend the paths of stars? Can something deserve the name of matter if it does not glow, does not reflect, and perhaps never directly touches an instrument, yet leaves unmistakable fingerprints in the structure of galaxies? These questions were not answered all at once. They accumulated slowly, often reluctantly, across centuries of argument and experiment. Long before modern cosmology spoke of dark matter and dark energy, there was already discomfort in the foundations of physics. Isaac Newton had given Europe a law of gravitation of astonishing power. With it, the same mathematical principle could describe an apple falling toward the earth and the moon circling the earth in its long, silent path. It was one of the greatest unifications in intellectual history. Yet buried inside that triumph was a problem that never quite disappeared. Newton could write down the law. He could show how gravitation behaved. But the deeper question of how one body might influence another across apparently empty space was far less satisfying. Historians and philosophers of science have long noted that Newton himself did not treat this kind of action at a distance as an easy or complete mechanical explanation. In other words, one of the founding achievements of modern physics already depended on a pattern that could be calculated more confidently than it could be understood. To appreciate how unsettling this was, it helps to picture the intellectual atmosphere of the 17th and 18th centuries. Many thinkers still hoped that the universe could be explained in thoroughly mechanical terms. Causes should be local, visible, contact-based, much like gears pushing gears, or particles colliding with particles. A cosmos governed by hidden influence seemed to threaten that ideal. If gravity worked across emptiness, then what was the emptiness doing? Was it truly nothing? Or was it carrying some unrecognized structure? Even before the 19th century, the modern mind was already being pressed toward a new possibility. Nature might not be reducible to the kinds of mechanisms that everyday intuition finds comfortable. The world might contain forms of order that operate without ever becoming visible in the ordinary sense. That thought did not arrive as a clean revelation. It arrived as an irritation, a conceptual splinter lodged inside an otherwise elegant theory. The history of invisible structures advances in just that way, through discomfort that cannot be ignored. When a theory succeeds too well for its own philosophical comfort, people begin to live with contradiction. They use the equations, trust the predictions, build ever more refined measurements, and carry on. But the unresolved question remains, waiting for another generation to look at it from a new angle. What Newton left uncertain would not be resolved by simply improving the law of gravitation in its existing form. It would require a much broader shift in how science imagined space, force, and physical reality. That shift began to gather force in the 19th century, especially in the study of electricity and magnetism, where invisible influence was even more intimate and immediate. Imagine yourself in a laboratory lit not by electric bulbs, but by daylight and flame, with coils of wire, glass apparatus, iron filings, magnets, and chemical smells hanging faintly in the air. Michael Faraday, who came from modest beginnings and had little formal training in advanced mathematics, became one of the great intuitive experimenters in the history of science. He had a rare gift for seeing patterns and phenomena that others still treated as isolated curiosities. In his hands, magnetism and electricity were no longer merely strange effects occurring between objects. He began to think of the space around those objects as physically important. With the idea of lines of force, Faraday gave a kind of imaginative body to invisible influence. He did not yet possess the full mathematical language that later theorists would bring to the subject. But he had something just as powerful in its own way: the conviction that the region around a magnet or a charged body was not a passive emptiness. It was a seat of real physical relations. That change was profound, though it can seem modest at first glance. If one object pulls on another, it is tempting to think only about the two objects. Faraday shifted attention to what lies between them. The surrounding space became active, structured, charged with possibility. That mental move would eventually transform physics. It suggested that reality might not be made only of solid things acting upon one another, but also of extended conditions distributed through space itself. A field, though invisible, could be real. It could store energy, transmit influence, and shape motion. This was a new kind of ontology, a new way of saying what the universe is made of. And like many powerful ideas, it did not arrive fully formed. It emerged through experiments, diagrams, visual imagination, and a stubborn trust that nature was revealing more than immediate appearances allowed. James Clerk Maxwell provided the next great deepening of this vision. Where Faraday had seen patterns in experiment and pictured lines of force, Maxwell supplied a mathematical framework capable of holding them together. In the middle of the 19th century, he showed that electricity, magnetism, and light were not separate provinces of nature after all. They belonged to a single connected structure, light itself. Perhaps the most familiar and symbolically powerful of all natural phenomena, turned out to be an electromagnetic wave. It is difficult to overstate the quiet radicalism of this realization. the visible became a special case of the invisible. What people saw streaming through a window or spilling over a landscape at dawn was, in a deeper sense, the behavior of a field. Space was no longer an empty container through which light traveled as a mere convenience. It was a domain in which physical structure lived and changed. By the late 19th century, physics had begun to learn a new humility. The world was proving less concrete, less directly mechanical, than many earlier thinkers had hoped. But it was also becoming more coherent. Invisible structures did not make nature more chaotic. They made it more intelligible. Fields allowed apparently separate phenomena to be understood together. This is one of the recurring patterns in the history of science. What first appears unsettling often later becomes clarifying. The mind resists a new kind of reality, then gradually discovers that the new reality explains more, unifies more, and carries more beauty than the older picture it replaces. It is worth dwelling on that emotional rhythm, because it lies beneath many of the scientific revolutions in this story. Discovery is not always the addition of a new fact. Sometimes it is the slow training of thought to inhabit a larger and less intuitive world. Then came Einstein, and with him another shift so deep that even the notion of a field would no longer be the full story. In 1915, after years of struggle, he completed the general theory of relativity, recasting gravity not as a force acting through space in the old sense, but as a manifestation of the curvature of space-time itself. This was not a small correction to Newton. It was a transformation in the background assumptions of physics. Space and time, once imagined as the fixed stage upon which matter moved, became part of the physical drama. They could stretch, bend, and participate in the behavior of the cosmos. The invisible structure shaping motion was now more abstract, yet also in some sense more intimate, because it was woven into the very arena of existence. In Einstein's universe, matter tells spacetime how to curve, and curved spacetime tells matter how to move. That elegant summary would come later. Living through the theory's birth was something messier. Pages of tensor mathematics, conceptual difficulty, and a long effort to think beyond inherited intuitions. The public memory of Einstein often compresses all of this into a single image of genius. But the real history is more human and more instructive. He wrestled with the mathematics required for a curved universe. He made detours and corrections. The path to general relativity was not a lightning strike, but a prolonged intellectual labor. That matters here because this documentary is not only about hidden structures in nature, it is also about the mental effort required to recognize them. Human cognition is adapted to middling scales, familiar objects, and practical movement through the world. It is not naturally adapted to fields that fill space, or to a four-dimensional geometry that bends under the presence of mass and energy. To think scientifically is often to learn how to distrust first impressions without losing contact with reality. It is a discipline of imagination guided by evidence. When the 1919 eclipse expeditions associated with Arthur Eddington helped bring Einstein's theory to international attention, the event acquired an almost mythic quality. Light from distant stars appeared to bend as it passed near the sun, just as general relativity predicted. Later, historians have reminded us that the evidence and its interpretation were more complex than popular retellings suggest. Even so, the deeper significance remains. A prediction about an invisible structure had been tested by watching visible light deviate from its expected path. Once again, the unseen did not present itself directly. It revealed itself through a trace, a shift, an alteration in something else. That is the recurring grammar of this story. Fields, curvature, missing mass, relic radiation, gravitational waves. None arrive as ordinary objects. They appear as signatures. By this point, a pattern begins to emerge across the centuries. Science repeatedly encounters a discrepancy between the world as it appears and the world as it behaves. An apple falls. A planet sweeps through the sky. Iron filings arrange themselves around a magnet. A beam of starlight bends near the sun. Galaxies in a distant cluster move too fast. A faint microwave hiss comes from every direction. A detector trembles in response to a ripple that passed through the Earth from some unimaginable collision far away. In every case, the essential work of understanding begins with the same quiet act: to trust the behavior even when the underlying structure is not yet visible. This has altered more than the content of physics. It has altered the psychology of inquiry. A mature scientific culture learns to live with entities that are first known only by inference. It develops standards of evidence for things that cannot be pointed to directly. It becomes comfortable with layered reality, with the idea that what is most consequential may not be what is most obvious. That intellectual discipline was hard-won. It required instruments, mathematics, experimental craft, and philosophical courage. It also required a gradual loosening of the old demand that the real must always resemble the visible. By the 20th century, that older demand had been weakened enough that physicists could speak seriously about fields permeating space, about space-time geometry, about invisible mass, and later about vacuum structure and quantum symmetries. The universe had not become less real. It had become deeper. And yet depth is never given all at once. Even now, the invisible remains partly veiled. We describe it with increasing precision, but often with lingering uncertainty about its underlying nature. That tension between knowledge and incompletion is one of the reasons this story retains its force. The more science uncovers, the more it reveals that reality is organized by frameworks that operate beneath immediate appearances. We do not stand outside those frameworks. We live inside them. Every falling object, every star, every atom, every beam of light participates in a universe whose most important structures often cannot be seen directly at all. Before we follow those structures into galaxies, fields, and the deep architecture of space-time, we need to return to the first great unease at the heart of modern physics. We need to go back to the moment when gravity itself became a triumph of knowledge and, at the same time, a profound mystery. In that tension, the journey truly begins. In the second half of the 17th century, the motions of the heavens still carried a kind of double character in the European mind. They were at once familiar and remote. People had watched the moon wax and wane for all of recorded history, had marked the wandering of planets, had seen comets appear as interruptions in an otherwise orderly sky. Yet the deeper logic behind those motions remained unsettled. Johannes Kepler had shown that planets moved in ellipses rather than circles, and Galileo had helped loosen the old Aristotelian picture of the cosmos. But there was still no single physical principle that seemed to bind the fall of earthly bodies to the great silent arcs of celestial ones. The earth and the heavens, though increasingly linked by observation, still retained something of their old separation. What Isaac Newton achieved was to close that distance with a degree of intellectual force that is difficult to exaggerate. With a single framework, he made it possible to think that the apple and the moon belonged to the same order. That unification, when it arrived, did not appear as a sudden flash detached from prior work. It emerged from a long accumulation of questions about motion, measure, and force. Newton inherited a world already transformed by careful astronomy, by the new mathematics of change, and by a growing confidence that nature could be described quantitatively. But inheritance alone does not explain the scale of what followed. In the Principia, published in 1687, Newton set out laws of motion and a universal law of gravitation that allowed the same mathematics to describe projectiles near the Earth, tides in the oceans, the paths of planets around the sun, and the behavior of comets moving in from the dark. This was not simply a set of useful formulas. It was a new kind of order. The cosmos no longer appeared as a collection of separate realms governed by different principles. It became, at least in outline, a single intelligible system. That coherence was one of the triumphs of modern thought, and it carried a deep emotional force as well. The universe began to seem less like a patchwork of mysteries and more like a structure that could be read. At first, the elegance of this achievement almost concealed the unease inside it. Newton had shown that gravitational attraction falls off with the square of the distance and had woven that relation into a structure of astonishing predictive power. From this came explanations for Kepler's laws, for the flattening of the Earth at the poles, for the precession of the equinoxes in approximate form, and for the rise and fall of tides under the combined influence of the moon and the sun. Here was a law that reached from the ground beneath one's feet to the edge of the known planetary system. It is easy, looking backward, to imagine that success of this scale must have felt final, but the very perfection of the law created a strange pressure. Newton had told the world how gravity behaves with extraordinary precision. Yet the question of what gravity is, in any deeper physical sense, remained disturbingly open. A body seems to attract another body across empty space. By what means? Through what medium? By what contact? That question mattered because the 17th century still lived under a strong mechanical ideal. Many natural philosophers hoped that the world, once properly understood, would resemble an immense machine whose causes could be traced through contact, impact, pressure, and transfer. The model was intuitive because it reflected the scale of ordinary life. A cart moves because a horse pulls it. A door opens because a hand pushes it. One billiard ball strikes another, and motion is passed along. Hidden influence acting through apparent emptiness seemed, to many minds, like a retreat into obscurity rather than an advance toward explanation. Even thinkers willing to accept Newton's mathematics could remain philosophically dissatisfied. A law of attraction might describe the pattern beautifully, but if no mechanism linked the bodies, had explanation truly been achieved? Or had the mystery merely been relocated into the language of force? Newton himself did not behave like a man entirely at ease with the implications of his own theory. Later generations sometimes remembered him as the master of certainty, the great geometer of the cosmos. But the historical Newton was more cautious and more troubled than that simplified image suggests. In private correspondence and in the tone of certain public remarks, one senses an unwillingness to present gravity as some obvious property of matter operating by direct magical reach. He resisted the idea that matter should simply possess an unexplained tendency to attract other matter across a void without mediation. His famous stance, often summarized through the phrase hypotheses non fingo, was not a declaration that the problem had vanished, but something closer to an admission of limits. He would describe the mathematical relations and leave the deeper cause unresolved rather than invent a mechanism he could not justify. This was an act of discipline, but it was also a sign of unease. One of the greatest scientific theories ever written rested on a phenomenon whose manner of operation remained obscure. For the generation that followed, this ambiguity became a point of sustained philosophical pressure. The success of Newtonian astronomy made it impossible to dismiss gravitation as mere speculation. Predictions worked too well. Comets returned when calculations said they would. Planetary motions could be analyzed with a confidence that earlier systems had not achieved. Yet success did not silence criticism from those who believed that all genuine causes had to be mechanical and local. Gottfried Wilhelm Leibniz, among others, objected to aspects of Newtonian attraction because it seemed to reintroduce occult qualities under a mathematical disguise. The language of occult here did not mean sorcery in the popular sense. It meant hidden, unexplained, insufficiently reduced to intelligible mechanism. That accusation reveals something important about the scientific mood of the time. The debate was not simply about whether the equations worked. It was about what kind of universe science was allowed to describe. Could nature contain real powers that were known only through their effects, long before their underlying carriers or media were understood? This tension between predictive success and explanatory discomfort shaped more than abstract philosophy. It influenced how educated Europeans imagined the fabric of reality itself. If gravitation acted through empty space, then emptiness no longer seemed empty in the old simple sense. Either bodies were mysteriously affecting one another at a distance, or the space between them possessed some role not yet properly grasped. The conceptual strain here is easy to miss because the modern reader is already used to fields, curvature, and invisible radiation. But in Newton's time, the thought that the gap between bodies might itself matter was still hovering just beyond articulation. Space had often been treated as a kind of passive stage, a container within which events occurred. Gravitational attraction forced the question of whether the stage was truly passive. Something seemed to be happening across it, through it, or perhaps because of some hidden order associated with it. The invisible had entered physics not as a speculative embellishment, but as a demand imposed by the success of measurement. There is also a psychological dimension to this moment that is worth lingering over. Human beings are usually more comfortable with mysteries that remain distant than with those that sit at the center of successful knowledge. A failed theory can be set aside. An incomplete theory that keeps working becomes harder to ignore. Newtonian gravitation had exactly this unsettling quality. It did not crumble under scrutiny. It deepened its hold. The more precisely the heavens were measured, the more indispensable the law became. And yet its physical basis remained veiled. This meant that scientists and philosophers had to learn a new intellectual posture. They had to accept, at least provisionally, that one could know a structure through its effects before one understood its inner nature. In practical terms, that meant trusting the mathematics. In deeper terms, it meant loosening an ancient bond between the visible and the real. A force could be real not because it resembled a familiar pushing mechanism, but because the world behaved as if it were there. Over time, this changed the meaning of explanation. In earlier natural philosophy, to explain something often meant reducing it to a contact process that imagination could almost picture. In the Newtonian world, explanation began to split into layers. One layer was mathematical and predictive. Another was physical and metaphysical. A theory might be complete enough in the first sense while remaining incomplete in the second. That distinction, once opened, would never entirely close. It became one of the hidden engines of modern physics. Again and again. Later scientists would find themselves in a similar situation. They would infer a deeper structure from what it did before they could state confidently what it was. In this sense, Newton's discomfort was not a temporary embarrassment on the way to clearer knowledge. It was the beginning of a new style of knowing, one in which inference outran intuition and reality revealed itself in forms the senses could not directly sponsor. The 18th century lived inside that new style while still trying to domesticate it. Newtonianism spread across Europe with extraordinary influence, shaping astronomy, mathematics, engineering, and the broader image of a lawful universe. At the same time, many thinkers continued searching for a more satisfying underlying account of attraction. Some imagined subtle fluids. Others proposed ethereal media filling space. There was no shortage of conceptual attempts to give gravitation or other forces a carrier that would make them feel less disembodied. These efforts are historically important, not because most of them survived, but because they show how hard it was to remain with a successful but philosophically incomplete idea. People wanted nature to become not only calculable, but imaginable. They wanted to know what sort of world they were inhabiting. Was it built from contact mechanisms too small to see, or from powers more abstract than common sense preferred? This desire for intelligibility did not disappear as science advanced. It simply migrated into new problems. As electrical and magnetic phenomena drew more sustained attention in the 18th and early 19th centuries, investigators encountered forms of action that seemed even less easy to picture in the old mechanical way. A rubbed glass rod could attract light objects without touching them. Magnets could order iron filings into elegant curved patterns that seemed to visualize some hidden arrangement in the surrounding space. Electrical discharges, sparks, shocks, and induced currents suggested processes that were real enough to be measured and harnessed, yet difficult to imagine as collisions of tiny bodies alone. The universe, it seemed, was full of structured influence. Newton had made one invisible order mathematically inescapable. Electricity and magnetism would make the problem broader and more immediate. The question was no longer only how planets moved at a distance. It was how forces seemed to inhabit the very spaces around ordinary objects. The transition from Newton's world to the age of fields was not a clean break. And that is part of what makes it so revealing. Newton did not solve the problem of invisible order once and for all. He established its legitimacy. He showed that a law governing unseen influence could organize vast regions of nature with unmatched power. That achievement gave later scientists permission, in a sense, to take invisible structure seriously without apology, so long as it proved itself through coherent effects. Still, the old unease remained active beneath the surface. Was gravitation a direct attraction between masses, or a sign that space contained a deeper organization? Were electric and magnetic actions also examples of hidden relations spread through the environment, rather than confined inside bodies? As instruments improved and experimental traditions matured, those questions became increasingly difficult to avoid. The path forward would depend not only on better equations, but on a new imagination of what occupies the intervals between things, seen from a distance. Newton's place in this story is therefore subtly paradoxical. He is both the great architect of classical certainty and the source of a productive unresolved problem. He gave modern science one of its most stable frameworks, and at the same time exposed a difficulty that framework could not fully absorb. That combination is one of the reasons his work continued to shape physics long after particular details were modified. Newton taught later generations that the universe could be mathematically ordered on a grand scale. But he also left them with a challenge that would push inquiry into stranger territory. The visible world was lawful, yes, but the law itself pointed beyond the visible. The apple fell, the moon curved in its orbit, and the numbers agreed. Yet beneath that agreement lay a silence. Gravity acted. The mind wanted to know how. By the beginning of the 19th century, that silence had become fertile. It no longer felt like an isolated defect in an otherwise complete system, but like the sign of a larger transformation in how physical reality would have to be conceived. The mechanical philosophy had not disappeared, but it was beginning to strain under the weight of phenomena that seemed to require more than impacts and collisions. In laboratories and lecture halls, in demonstrations with wires, magnets, batteries, and coils, a different picture was slowly taking shape. The hidden order of the world might not reside only in bodies themselves, but in the regions around them, in extended conditions distributed through space. To understand that shift, we have to move away from celestial mechanics and into a more intimate theater of discovery, where invisible influence could be made to leave patterns in iron filings and currents in wire, and where the old emptiness between things began, quietly, to fill. As the 19th century advanced, the old mechanical picture of nature came under a new and persistent kind of pressure. It did not collapse all at once. It was simply asked to explain more than it had been built to bear. In drawing rooms, lecture theaters, workshops, and laboratories, electricity and magnetism produced effects that were at once precise and elusive. A spark leapt across a gap. A needle trembled and aligned itself with the earth. Iron filings scattered over a sheet of paper formed curved patterns around a magnet, as if some invisible order had quietly arranged itself in the space above the table. At first, these phenomena could still be treated as curiosities, strange but local, the sort of things one might hope eventually to reduce to hidden impacts or subtle fluids. Over time, however, the phenomena multiplied, and with them came an unsettling suggestion. Perhaps the most important part of these events was not only the bodies involved, but the space between them. It is difficult to understand Michael Faraday without first understanding how unusual he was in the culture of science of his age. He was not formed in the mold of the great university mathematician. Born in 1791 to a family of modest means, apprenticed to a bookbinder in his youth, he entered science through reading, listening, and an extraordinary discipline of attention. When he attended the lectures of Humphrey Davy and later joined the Royal Institution, he carried with him neither the social polish nor the formal mathematical training that many would have considered essential to high science. What he did possess was something rarer. He had an ability to follow physical phenomena with a patience so sustained that patterns began to reveal themselves where others still saw disconnected effects. Faraday's notebooks and experiments show a mind that did not rush to impose a system too quickly. He preferred to stay close to the behavior of nature, to let repeated observation shape the language in which explanation would eventually become possible. That habit mattered because electricity and magnetism, in the early decades of the 19th century, were not yet unified subjects. They consisted of many partly understood effects gathered from different experimental traditions. There were electrical attractions and repulsions, sparks from friction machines, galvanic currents from chemical cells, the deflection of magnetic needles, and the growing realization that these phenomena might somehow be related. Oersted's discovery in 1820 that an electric current could deflect a compass needle was one of the decisive moments in that transformation. It suggested that electricity and magnetism were not separate curiosities after all, but adjacent expressions of a deeper physical order. Ampere, Arago, and others pursued the implications energetically, bringing mathematics and experiment to bear on a subject that was suddenly becoming much larger than anyone had expected. For Faraday, this expanding field of inquiry offered not only new effects to study, but a new way to ask what sort of thing a force really is. The question became even more urgent when Faraday began the work for which he would be remembered most deeply. In 1831, after years of effort and repeated experimental variations, he discovered electromagnetic induction. A changing magnetic condition could generate an electric current. A current in one coil could induce a current in a nearby coil, even without direct contact, provided the conditions were right. Here again was invisible influence, but not of the old Newtonian kind. This was active, transformable, almost spatial in its behavior. The crucial point was not simply that one object affected another. It was that the effect depended on changes in the surrounding arrangement. When the magnetic environment shifted, the electrical response appeared. The relation seemed to live in the configuration itself. This led Faraday toward one of the most important intellectual moves in the history of physics. Instead of imagining forces as mysterious pulls passing instantaneously from one body to another, he began to treat the space around bodies as the true seat of physical action. At first, this remained partly a visual and experimental language rather than a fully formal one. Faraday spoke of lines of force, and to later ears that can sound metaphorical, almost poetic. But for him, the phrase was not merely a convenient picture. It was an attempt to express a conviction about reality. The curves traced by iron filings around a magnet were not, in his view, just a way of illustrating where an influence happened to be strong or weak. They were clues to the arrangement of something physically meaningful in the space itself. The region around a magnet, or around an electric charge, was not inert emptiness waiting for bodies to pass through it. It possessed order, direction, and capacity. Energy could be stored there. Effects could be transmitted through it. Motion could be guided by it. This was a startling reorientation of thought because it shifted the center of explanation away from the objects alone and toward the continuum in which they were embedded. Such a move did not come easily to everyone. To many mathematically trained physicists, Faraday's style could seem insufficiently rigorous, too dependent on intuition and experimental imagination. He was not careless, but his rigor was of a different kind. It came from repetition, sensitivity to apparatus, and an almost tactile familiarity with phenomena. He drew, rotated, connected, and reconnected. He watched needles twitch and sparks appear. And from those patterns, he inferred that the old language of direct action between bodies was no longer adequate. Over time, this way of thinking began to change the conceptual atmosphere of physics. A field, though the word itself would gather its full meaning gradually, was beginning to emerge as a new kind of physical reality, not a solid substance in the ordinary sense, and not merely a bookkeeping device, but an extended condition of space with measurable consequences. The invisible was becoming less like an embarrassment in theory and more like the true medium through which the visible world was organized. Faraday's own temperament made him especially suited to this transition. He was cautious, deeply religious, resistant to needless speculation, and reluctant to outrun what experiment could sustain. That combination may seem unlikely in a conceptual revolutionary, yet it gave his innovations a distinctive credibility. He did not propose invisible structures because he was attracted to abstraction for its own sake. He proposed them because the behavior of nature seemed to demand them. There is a difference between inventing an unseen world and becoming convinced that the seen world cannot be understood without one. Faraday belonged to the second tradition. In his studies of induction, electrolysis, diamagnetism, and the relation between light and magnetism, he continued to encounter the same pattern. The deeper one looked, the less plausible it became to think of space as a passive void. Something was distributed through it, structured through it, and made active by the arrangement and motion of matter. This raised a difficulty that was also an opportunity. Faraday's ideas were physically fertile, but they lacked the kind of mathematical expression that would allow them to be extended, generalized, and woven into a single theoretical framework. In the middle decades of the 19th century, that task fell above all to James Clerk, Maxwell. If Faraday's genius lay in seeing physical relations in the laboratory before formal language existed to contain them, Maxwell's genius lay in recognizing that those relations could be expressed mathematically without losing their physical depth. Born in 1831, the very year Faraday discovered induction, Maxwell came from a different world. He was academically trained, mathematically gifted, and capable of moving between abstraction and physical intuition with unusual ease. Yet what made his contribution so powerful was not that he replaced Faraday's vision with something colder or more exact. It was that he found a way to preserve Faraday's central insight and give it a form capable of transforming all of physics. Maxwell's path into electromagnetism was not simply that of a mathematician tidying up an experimental field. He had to decide what exactly. Faraday's lines of force were telling science about nature. In a series of papers beginning in the 1850s and continuing through the 1860s, he worked toward a description in which electric and magnetic processes were not isolated actions between separate bodies, but interlocking states of a continuous medium or field. At first, he sometimes used mechanical analogies, including fluid-like and gear-like models, not because he believed those models were literally true in all respects, but because they helped him reason his way into equations. This is important historically, because it shows that even a theorist as advanced as Maxwell still needed transitional imagery. The human mind often reaches a new concept by way of older pictures, then slowly sheds the scaffolding once the deeper structure becomes clear. As a result, Maxwell's equations did not spring into existence as pure symbols detached from intuition. They emerged from a long effort to translate Faraday's physical imagination into a mathematically coherent universe. The decisive consequence of that translation was extraordinary. Once electric and magnetic fields were written into a unified mathematical form, the equations suggested that disturbances in those fields could propagate through space as waves. When Maxwell calculated the speed of such waves from known electrical and magnetic constants, the result came out close to the measured speed of light. The implication was hard to resist. Light itself was an electromagnetic phenomenon. What generations had treated as something separate, perhaps as rays or particles or a distinct luminous substance, now appeared as a vibration of an invisible field pervading space. This was one of the quiet turning points in intellectual history. The visible became a local expression of a deeper, invisible order. Every sunrise, every reflection on water, every star seen in the night sky was now bound to a structure that could not itself be seen. only inferred through its behavior. A field was no longer merely a useful way to map forces around objects. It had become the medium of light itself. With that realization, the old question of emptiness took on a new depth. If light is a wave, then in what does it wave? 19th century physicists often answered with the concept of the luminiferous ether, a subtle medium filling space and carrying electromagnetic disturbances. For a time, this seemed natural. Waves in ordinary life require something to wave through, whether air for sound or water for ripples. The ether offered a way to make Maxwell's theory feel more imaginable. Just as earlier, mechanical analogies had helped bridge the conceptual gap. Yet even before later experiments and Einstein's work would transform the issue. One can already see the central theme of this documentary taking on sharper form. Space could no longer be treated as nothing, whether one described it as containing an ether or, more abstractly, as the domain of fields. It had acquired structure, something physically meaningful extended through regions where common sense had once seen only emptiness. This was more than a technical advance. It altered the hierarchy of the real. In older ways of thinking, bodies were primary and the spaces between them secondary. Now the relation began to reverse. The field surrounding a charge or a magnet could be treated as primary in certain explanations, while the objects became sources or disturbances within a larger continuum of order. This change also modified how causation itself was imagined. Instead of a body acting mysteriously on another distant body, one could think of local changes in a field propagating through space and influencing matter step by step. The result was both more subtle and, in a way, more satisfying than the older picture. Action no longer had to leap across a void. The void had become structured. Locality could be preserved, but only because space itself had become physically active. This was a major conceptual reconciliation, one that helped make invisible structure feel not like a philosophical concession, but like a more adequate account of reality. Even so, the transition was not simply from confusion to clarity. Maxwell's theory was powerful, but it also generated new uncertainties. The equations united electricity, magnetism, and light with stunning elegance. Yet the ontological status of the underlying medium remained unsettled. Was the ether real in a mechanical sense, with properties that might someday be directly specified? Or was the field itself now the more basic concept? Scientists of the late 19th century lived inside that ambiguity. Some preferred mechanical models because they promised continuity with older intuitions. Others became more willing to treat the equations and their physical implications as fundamental, even when no familiar picture could fully accompany them. This tension matters because it reveals how scientific understanding often grows. A theory can become indispensable before its deepest interpretation stabilizes. Nature can be used, measured, and predicted even while the mind continues negotiating what kind of world the theory implies. For those working in laboratories, however, the power of the new field concept was increasingly difficult to deny. It made sense of induction. It made sense of electromagnetic waves. It suggested continuity between the local behavior of apparatus and the vast travel of light across space. In 1887 and 1888, Heinrich Hertz generated and detected electromagnetic waves in the laboratory, providing striking confirmation that Maxwell's theory described something physically real rather than merely formal. Tiny sparks leaping in a detector across the room were enough to show that invisible waves could travel through space and be received elsewhere. This was not just a victory for a set of equations. It was another lesson in how the unseen reveals itself through signatures. You do not observe the field directly as you observe a table or a stone. You observe what it does. You detect its capacity to carry energy, structure motion, and connect events across space. By the end of the 19th century, a new image of nature had taken hold, though not without lingering tensions. The world no longer seemed built only from hard bodies moving through an indifferent void. It appeared instead as a layered reality in which space was filled with active relations, and in which fields could organize the behavior of matter just as decisively as matter itself. This did not make the universe less intelligible. In many ways, it made it more so. Phenomena once treated as scattered curiosities had been drawn into a single framework: electricity, magnetism, light, induction, radiation, and wave propagation were now understood as aspects of one connected order. The mind had been asked to accept an invisible structure more pervasive than any previous one, and in return, it received a deeper unity than classical mechanics alone had offered. What changed in this period was not only the content of physics, but the trained habits of scientific imagination. Faraday had taught science to take seriously the possibility that the space around objects is physically meaningful. Maxwell had shown that this possibility could be written into one of the most elegant theoretical systems in modern history. Together, they did more than discover new phenomena. They changed the question of what kind of thing space is, no longer merely an empty interval separating bodies. It had become the seat of forces, waves, and energy. The universe was beginning to look as though its most important structures were not always the objects moving within it, but the invisible arrangements through which those objects related to one another. That shift prepared the mind for even stranger revisions to come, because once space is granted structure, it is only a short step. Historically speaking, to wonder whether space and time themselves might participate even more deeply in the drama of the cosmos. And so the story moves toward a new transformation. Fields had filled the apparent emptiness between bodies with physical meaning, but they had not yet exhausted the question of what space itself might be. The old Newtonian stage had become active, yet it still remained, in some sense, a stage. In the years ahead, that assumption too would begin to give way, as one physicist after another followed inconsistencies in motion, light, and gravitation toward a view of the universe in which the geometry of reality itself would no longer remain fixed. By the closing years of the 19th century, the world described by physics had become more unified, but it had also become more unstable at the foundations. Maxwell's fields had given invisible structure to space, yet the deeper status of that structure remained uncertain, and the relation between electromagnetism and mechanics was no longer as comfortable as many had hoped. Light seemed to travel as an electromagnetic wave, but the old picture of motion through a fixed background was beginning to strain. Experiments such as those associated with the ether drift problem did not deliver the expected signs of a medium through which the Earth was moving. And although these results did not instantly overturn older views, they intensified the feeling that something basic was unsettled. In that atmosphere, the young Albert Einstein entered physics not as a specialist of gravitation, but as someone increasingly dissatisfied with inherited assumptions about motion, light, and the structure of physical law. His 1905 special theory of relativity had already altered the terms of the discussion by eliminating the need for a preferred frame of rest and insisting that the laws of physics should take the same form for all inertial observers. But that theory radical as it was, still left gravity standing outside the new order. It worked for bodies moving uniformly, not for the more universal fact that the world is full of falling, orbiting, accelerating things. The path from special relativity to general relativity did not begin with a finished vision. It began with a problem that Einstein himself later described as the happiest thought of his life. Around 1907, he began reflecting on the equivalence between inertial mass and gravitational mass. The empirical fact that objects fall with the same acceleration when other influences are ignored. This was one of those facts that had long been known in practice without having yielded its full conceptual meaning. Einstein realized that for a person in free fall, gravity would seem to disappear locally, while for a person in an accelerating frame, gravity-like effects would seem to appear. At first, this was not yet a complete theory, but it suggested a profound shift in perspective. Gravity might not be a force in the old sense at all. It might instead be connected to the very conditions under which motion is described, to the geometry of the arena itself. The equivalence principle opened a door, but it did not tell Einstein how to walk through it. It gave him a clue of almost unbearable depth and left him with the hard labor of finding the mathematics that could make the clue into a theory. That labor took years, and it is important to linger there, because the real history of general relativity is not the clean legend of a single moment of genius. Einstein had extraordinary physical intuition, but the mathematical language required for a fully general theory of gravitation was not part of his earlier formation. As he moved beyond the flat space-time of special relativity, he increasingly needed tools associated with differential geometry and tensor calculus, fields shaped by Riemann, Christoffel, Ricci, Levi-Civita, and others. Einstein Online notes that between 1908 and 1915, he developed general relativity step by step, with crucial help from people around him, especially Marcel Grossmann, his former fellow student, who guided him toward the mathematics he needed. This historical detail matters because it restores texture to the story. Einstein was not simply thinking harder than everyone else in isolation. He was learning, discarding, revising, and depending on collaborators and mathematical traditions that had matured before, he knew how essential they would become as a result. The years before 1915 were full of partial advances and genuine wrong turns. Einstein and Grossmann produced the so-called Entwerf theory, which captured part of what Einstein was seeking, but did not yet have the final generally covariant field equations. Later, historical studies of Einstein's Zurich notebook and related documents show that he came remarkably close to the final structure earlier than he realized, then moved away from it before returning. That is one of the most revealing aspects of the episode. The final theory was not hidden because it was inconceivable. It was hidden because too many constraints were in play at once. Einstein wanted a theory that reduced to Newtonian gravity in the appropriate limit, matched physical intuition, respected the equivalence principle, and possessed the right mathematical generality. Each demand pulled on the others. Over time, the problem became less like solving a puzzle and more like navigating a narrow pass through a landscape of almost solutions. This is often how deep science proceeds. The final answer is not simply waiting intact. It has to be separated from neighboring ideas that look plausible for a long time. What made the task especially difficult was that Einstein was not merely adding a correction to Newton. He was altering the status of space and time themselves. In the Newtonian picture, the stage of the universe remained fixed while bodies moved and forces acted. Even after Maxwell, that stage could still be treated as something like a container. albeit one filled with fields and perhaps an ether. Einstein's developing insight pushed further. If acceleration and gravitation were deeply related, and if the laws of physics had to hold under broader changes of motion and coordinates, then geometry itself had to enter the heart of physics. Gravity would no longer be described as a pull exerted across space. Instead, mass and energy would shape space-time, and bodies in free fall would follow the natural paths made available within that curved structure. Britannica's overview of general relativity captures the central idea succinctly. Gravity becomes a geometric phenomenon arising from the curvature of space-time. But to reach that clarity in 1915 was to cross a major intellectual threshold. It meant that what people had once imagined as the most passive background feature of reality had become active, dynamic, and physically consequential. One sign that Einstein was approaching the right path came from an old astronomical irritation that had never been fully resolved: the perihelion of Mercury, the point of closest approach in its orbit around the Sun, advanced slightly more than Newtonian theory could account for. Once the perturbing influence of the other planets was included. During the 19th century, one proposed response was to imagine an unseen planet, Vulcan, orbiting closer to the Sun and producing the missing effect. That hypothesis never found secure observational support, but the anomaly remained. Britannica notes that in one of Einstein's November 1915 papers, general relativity gave the correct explanation for Mercury's anomalous perihelion precession. This mattered not only because a long-standing puzzle was solved, but because it showed that the new geometric theory could recover a stubborn detail of planetary motion without adding hidden bodies or ad hoc fixes. The old invisible planet was no longer needed. The explanation moved from unseen matter within Newtonian space to a new structure of space-time itself. The month of November 1915, therefore, has an almost compressed, breathless quality in the historical record. Einstein submitted a sequence of papers to the Prussian Academy, gradually refining the field equations until he arrived at the form now recognized as the foundation of general relativity. When people later speak as if the theory appeared in a single stroke, they erase the texture of that month and the many years before it. In reality, Einstein was working under intense intellectual pressure, with competing formulations, mathematical obstacles, and the awareness that David Hilbert was also pursuing a related route. Yet, the theory that emerged was more than a local achievement. It offered a new account of gravitation in which matter and geometry could no longer be separated in the old way. Free fall became, in essence, motion along geodesics, the straightest possible paths in curved space-time. This did not make the world simpler to imagine, but it made it more internally coherent. The need for gravity to reach across a void in the Newtonian sense began to dissolve. There was no longer the same kind of action at a distance, because the geometry through which motion unfolded had itself been altered. Even once the equations existed, the new theory still had to be made legible to the scientific community and, eventually, to the broader public. Einstein published his major review article, The Foundation of the General Theory of Relativity, in 1916, providing a fuller exposition once the theory had matured. Yet understanding did not spread instantly, and acceptance was neither automatic nor universal. General relativity was mathematically demanding, conceptually unfamiliar, and still awaiting decisive empirical tests beyond Mercury. This raised a problem that often accompanies revolutionary theories. How does a scientific community learn to trust an idea that is elegant and suggestive, but also abstract enough to seem almost detached from ordinary physical intuition? In part. The answer lay in its predictions. General relativity implied not only the Mercury result, but also the bending of light by gravity and the gravitational redshift of light. These effects offered the possibility that geometry, though invisible, could leave measurable marks on visible phenomena. That was exactly the kind of bridge the history of physics had used before. Invisible structure would again become credible by changing what could be seen. The most famous of those tests came with the solar eclipse of 29th May 1919. The underlying idea was beautifully simple, though the observations themselves were difficult. If space-time is curved by the sun's mass, then light from distant stars passing near the sun should follow that curvature and appear slightly displaced from where the stars would otherwise be seen. Under ordinary conditions, the sun's glare made such measurements impossible, but a total eclipse briefly removed that obstacle. Astronomer Royal Frank Dyson recognized the opportunity, and expeditions were sent to Sobral in Brazil and Principe off the west coast of Africa, with Arthur Eddington playing a leading role in the public and scientific story that followed. The historical importance of the eclipse lies partly in the data and partly in the symbolism. In the aftermath of the First World War, British expeditions were helping test the theory of a German physicist. The intellectual world was fractured by recent violence. Yet here was a moment in which international science still sought common standards of evidence. At the same time, historians have worked carefully to complicate the simplified legend that the 1919 eclipse instantly and unambiguously proved Einstein right beyond doubt. The Royal Society Historical Analysis emphasizes that the results were more nuanced than the myth suggests. Some of the observational material was of higher quality than others. Measurement difficulties were real, and later retellings often smoothed over those complexities in favor of a cleaner narrative of triumph. That correction is not a dismissal of the importance of 1919. Rather, it makes the event more historically honest and, in some ways, more interesting. The eclipse mattered because it was a serious test, because it became a powerful public moment, and because it helped make general relativity internationally visible. But science rarely moves by a single theatrical confirmation. It advances through an accumulation of evidence, argument, reinterpretation, and improved measurement. Even here, the story follows the deeper pattern of this documentary. An invisible structure was not seen directly. It was inferred because light itself arrived slightly altered by the geometry through which it had traveled. The public response, however, was immediate and dramatic in its own way. Newspapers seized upon the idea that Newton had been overturned and that a new genius had redrawn the universe. Einstein became an international symbol, though the fame often simplified the theory beyond recognition. Behind the headlines stood a quieter transformation in scientific understanding. Space and time were no longer stable background coordinates against which events could be measured from a distance. They had become part of the causal fabric of the world. A ray of light passing near the sun, the orbit of Mercury, the ticking of clocks and gravitational fields, all were now tied to the geometry of space-time itself. That shift altered not just one branch of physics, but the entire meaning of physical explanation. The universe was no longer a collection of things in a container. The container had become dynamic, relational, and shaped by the contents within it. In that sense, Einstein extended the revolution begun by Faraday and Maxwell. They had made space active. Einstein made its geometry physical. There is also a human lesson in the way general relativity came into being. Einstein's achievement depended on intuition, yes, but also on frustration, revision, collaboration, mathematical apprenticeship, and the willingness to remain with a problem even when the path forward was unclear for years. The psychology of this matters because it counters a persistent myth about science, especially in stories centered on famous individuals. Transformative theories often look inevitable after the fact. Living through them feels very different. It feels partial, fogged, improvised, burdened by errors that only later seem obvious. Einstein's struggle with the mathematics of gravitation, his movement toward and away from the final equations, and the gradual nature of empirical confirmation all remind us that scientific revolutions are not clean events. They are extended acts of disciplined imagination, grounded in the stubborn demand that reality must eventually cohere, even if the mind must be retrained to perceive how. By the early decades of the 20th century, one enormous consequence of this retraining was clear. The old Newtonian stage had lost its immobility. Space and time had become dynamic participants in the behavior of the cosmos, capable of bending, stretching, and guiding the motion of matter and light. Yet this did not close the story of invisible structure. In one sense, it opened it wider. Once geometry itself had become physical, the universe could no longer be treated as a simple backdrop decorated by stars and planets. Large systems might now conceal properties that were not obvious from their visible contents alone. Motion might reveal deeper structure than appearance suggested. And as astronomers turned their instruments toward nebulae, galaxies, and clusters on scales far beyond the solar system, they would begin to encounter a new and unsettling discrepancy. The universe, it seemed, was about to become heavier than its light. As astronomers pushed their attention beyond the scale of the solar system and out toward the larger architecture of the universe, they entered a domain where light no longer seemed to tell the whole truth. Galaxies could be photographed, their spectra measured, their motions estimated, and clusters of them mapped as immense systems suspended across distances that would once have been unimaginable. Yet the more these systems were treated as physical structures rather than mere luminous ornaments in the sky, the more a new kind of discrepancy began to emerge. Motion and visible matter did not always agree. The universe, on its largest scales, was starting to behave as though much of its weight was hidden. That realization did not arrive in one clean stroke, and it was not immediately understood in modern terms. It gathered slowly, from dynamical puzzles that at first could still be mistaken for measurement error, incomplete theory, or the ordinary untidiness of astronomical work. Over time, however, those puzzles refused to disappear, and the visible universe began to look like only the bright surface of something much larger. The first famous step in that direction came in 1933, when Fritz Zwicky studied the Coma cluster and applied the virial theorem to the motions of its galaxies. He used their observed redshifts to estimate how fast the galaxies were moving within the cluster, then compared that motion to the amount of visible matter that seemed present. What he found was deeply uncomfortable. The cluster appeared to require far more mass than its stars and luminous material could account for if it was to remain gravitationally bound. Zwicky concluded that there must be a large amount of unseen matter contributing to the system's gravitational glue, and he called it dunkle materie, dark matter. The phrase is so familiar now that it can seem inevitable, but at the time it named not a well-established substance, but a missing component inferred from a mismatch between motion and light. The cluster was behaving as if it were heavy in a way that its brightness did not reveal. Zwicky himself was a figure almost designed to complicate the history that later formed around him. He was brilliant, abrasive, original, and often difficult for colleagues to absorb into any conventional academic mold. The American Museum of Natural History describes him as bold and visionary, and notes that he was far ahead of his time on dark matter, supernovas, neutron stars, and even gravitational lenses, while also entertaining ideas that many contemporaries found eccentric. That combination mattered. Insight does not always arrive in a socially convenient form. Zwicky's personality helped make him memorable, but it may also have made it easier for the astronomical community to leave some of his more unsettling suggestions at the margins for a while. The dark matter problem was not dismissed outright, yet it did not immediately become the organizing mystery of 20th century astronomy. It remained one of those difficult results that could be acknowledged without being fully absorbed. Part of the reason was that astronomy in the 1930s did not yet possess the broader body of evidence that would later make the case compelling. A discrepancy in one cluster, however suggestive, could still be treated as a local difficulty. Distances to galaxies were uncertain by modern standards. Mass estimates were crude. Clusters were complicated systems, and astronomers were rightly cautious about converting one bold inference into a universal conclusion. The APS Historical Review of Dark Matter emphasizes that the history of the subject is not a straight line from Zwicky to modern consensus, but a gradual process in which cluster dynamics, galaxy rotation curves, and later cosmological evidence accumulated over decades. This gradualism is important because it shows how science often treats the unseen. A new invisible component becomes plausible only when multiple lines of evidence begin converging from different observational directions. Until then, even a correct idea may linger in a state of half-recognition. Even while Zwicky's work waited for stronger company, other astronomers were beginning to notice related tensions on smaller scales. Studies of galaxies in the 1930s and later decades hinted that luminous matter might not account fully for the observed motion of stars and gas. But the problem was difficult, because a galaxy is not a simple object. Its light is spread through stars, dust, and gas. Its orientation can complicate measurement, and its mass distribution cannot be read directly from a photograph. To infer the gravitational structure of a galaxy, astronomers had to measure how quickly different regions rotated and compare those speeds with what visible matter should produce. In a simple Newtonian picture, one might expect the outer parts of a galaxy to rotate more slowly once most of the luminous mass lay inside the orbit, much as planets farther from the sun move more slowly. Yet as better instruments and spectral techniques developed, nature again began to refuse that expectation. The outer regions did not always behave as though the visible center contained most of the mass. This was the setting into which Vera Rubin eventually stepped, bringing with her a style of science very different in temperament from Zwicky's, but equally consequential. Rubin's route into astronomy had its own obstacles. Carnegie's Historical Remembrance notes that she became a groundbreaking figure, in part because she persisted in a field that often excluded women from the same opportunities given to men, including, for a time, access to major observatories. Her work with Kent Ford, whose image tube spectrograph made it possible to measure faint galactic spectra with new precision, allowed the rotation problem to be studied in a deeper way than before. Their 1970 study of Andromeda and the work that followed through the 1970s and into 1980 showed something remarkably persistent. Stars and gas in the outer parts of spiral galaxies were moving much faster than a simple accounting of visible matter seemed to permit. Instead of dropping off in the expected way, the rotation curves tended to remain strikingly flat. The importance of a flat rotation curve becomes clearer when one lingers over the reasoning behind it. If most of a galaxy's mass were concentrated where most of its light is, then the orbital speed of stars far from the center should decline with distance once one moved beyond the bulk of that luminous mass. This is the intuition familiar from planetary motion in the solar system. Rubin and her collaborators found that galaxies did not generally behave that way. The outer stars kept moving at roughly similar speeds, as if additional mass continued extending outward well beyond the visible disk. The galaxy, in other words, seemed to sit inside a much larger halo whose presence could not be read directly from starlight. Carnegie's summary of Rubin's work states that over the decade they examined dozens of galaxies and repeatedly found the same pattern, evidence for what Rubin called non-luminous matter. At that point, the problem was no longer an isolated curiosity. It had become a recurring structural feature of galaxies themselves. Rubin's role in this history is important not only because of the data, but because of the way she inhabited scientific uncertainty. The surviving institutional and oral history portrayals of her emphasize persistence, generosity, and intellectual steadiness. She did not present herself as a conqueror of mystery. She worked with patience, built cases from repeated observation, and allowed the weight of the evidence to accumulate. This style of discovery matters in a documentary like this one, because dark matter did not enter astronomy as a dramatic revelation that everyone immediately recognized. It entered as a pattern too consistent to ignore. Galaxy after galaxy behaved as though most of its gravitating mass was not where the light was brightest. The visible universe, once again, was being asked to explain more than it could bear. By around 1980, the dark matter problem had changed status. Carnegie's retrospective goes so far as to say that by then, the case for dark matter was undeniable. And while scientists continued debating the details of its amount, distribution, and physical nature, the broader dynamical discrepancy had become difficult to deny. Galaxies appeared to live inside extended dark halos. Clusters still seemed too heavy for their light. The old idea that one could estimate the universe's gravitating content from luminous matter alone had been badly weakened. Yet even at this stage, astronomy had not simply exchanged one certainty for another. Naming dark matter did not explain what it was. It only acknowledged that something unseen behaved gravitationally, as though it dominated the mass budget of large systems. That distinction is crucial. Dark matter was first a dynamical inference, not a direct detection. Science knew the structure of the problem before it knew the nature of the thing causing it. That gap between behavior and identity opened the door to one of the most persistent debates in modern astrophysics. Perhaps there really was unseen matter. Or perhaps gravity itself behaved differently on galactic and larger scales than Newtonian or even standard relativistic intuition suggested. The APS review notes that alternatives such as modified Newtonian dynamics, or Amondi, arose precisely because the observed discrepancies seemed systematic and deep. Rather than adding hidden mass, these approaches attempted to alter the laws governing motion or gravity in the low acceleration regime characteristic of galaxies. This was not an irrational detour. It was a serious response to an underdetermined problem. If light and motion do not agree, one can either add unseen gravitating substance or revise the law connecting gravity to motion. The history of dark matter is therefore also a history of scientific restraint. Astronomers and physicists did not all rush in one direction. They explored competing ways of making the universe cohere. Over time, however, the evidence for dark matter began to widen beyond rotation curves and cluster dynamics. One of the most powerful tools in that widening was gravitational lensing, the effect predicted by general relativity in which mass bends the path of light from more distant objects. NASA's overview of dark matter stresses that while dark matter does not interact with light in the ordinary way, its gravity can still bend light from background galaxies. And studying those distortions allows astronomers to infer where mass is distributed. This mattered because lensing offered a way to map gravitating structure independently of how brightly matter shone. It turned the universe into its own measuring instrument. Mass could now be traced not only by the motion it induced in stars and galaxies, but by the way it warped the light of objects behind it. In the history of invisible structure, this is a familiar kind of advance. The unseen becomes more credible when it leaves multiple, independent signatures. The bullet cluster became one of the most famous and visually striking examples of this logic. In this colliding system of galaxy clusters, astronomers could distinguish several different components. There were galaxies visible in optical light, and there was hot intracluster gas visible in X-rays, representing much of the normal baryonic matter. During the collision, that hot gas interacted strongly and slowed, while the galaxies, which are mostly empty space relative to one another, pass through with much less resistance. Chandra's explanatory material notes that the concentration of mass in the system can be mapped using gravitational lensing, and that most of the mass inferred in this way is separated from the hot gas. The dominant visible ordinary matter, the result is conceptually powerful. The place where most of the gravity seems to be is not the same place where most of the luminous baryonic matter ends up after the collision. Mass and light have come apart in a way that is difficult to ignore. This does not mean that the bullet cluster ended all debate by itself, and it is better historically to resist that simplification. What it did was provide an unusually vivid system in which different components of a cluster collision behave differently enough that their separation could be studied. Within the dark matter interpretation, the visible gas is slowed by electromagnetic interactions, while the largely collisionless dark matter passes through more freely and leaves the dominant lensing signal near the galaxies. For supporters of modified gravity approaches, the bullet cluster became a serious challenge because it is difficult to explain why the inferred gravitational potential is offset from most of the normal matter. The system therefore did not eliminate all alternative thinking, but it sharpened the asymmetry in the evidence. Dark matter was no longer just an abstract accounting device for missing mass. It was beginning to look like a distinct, spatially distributed component of cosmic structure. What makes this history so compelling is that each stage changed the way astronomers thought about matter itself. In ordinary life, matter is what shines when heated, what reflects light, what resists touch, what can be gathered, weighed, or seen. Dark matter, by contrast, entered science through none of those familiar routes. It was never first encountered as a substance in the laboratory, nor as a new spectral line, nor as an object whose surface or interior could be directly imaged. It entered as behavior. It entered as galaxies rotating too fast, clusters holding together too tightly, and background light bending, as though far more mass were present than the visible universe declared. This kind of arrival has a special philosophical weight. It asks science to widen the idea of what can count as matter. just as earlier generations had to widen the idea of what can count as force or field. The invisible once again became real, not by resembling familiar objects, but by organizing the world more successfully than familiar objects could. There is also a quieter emotional rhythm beneath the technical history. Zwicky's early inference stood for years without full assimilation. Rubin's measurements made the problem intimate and systematic. Lensing and cluster collisions made the gravitational structure increasingly map-like and spatial. At each step, the evidence became less local and more architectural. The universe was not merely sprinkled with a few puzzling systems. It seemed built inside a hidden scaffolding of mass. Caltech's dark matter overview describes Zwicky's original insight as the realization that something else was acting like glue to hold clusters together. And that metaphor remains useful precisely because it captures what the visible universe seemed unable to do on its own. Gravity was binding luminous structures into larger systems whose cohesion demanded more than starlight. The cosmos, in this emerging picture, was heavier than its brightness. By the late 20th century and into the 21st, dark matter had become a central ingredient of mainstream cosmology. Even though its microscopic identity remained unknown, that unresolved status is part of what gives the subject its strange power. The scientific community can describe where dark matter seems to be, how much of it large systems appear to require, and how it helps explain the formation and stability of cosmic structures, while still lacking a direct, universally accepted account of what kind of particle or substance it might be. In this sense, dark matter belongs fully to the tradition this documentary has been tracing from the beginning. Reality first becomes legible through pattern, then through theory, then through multiple converging effects, and only sometimes much later through direct physical identification. Sometimes the final identification remains out of reach for a very long time. The structure is there before the essence is named. And yet even this was not the end of the story. Because once astronomers began accepting that unseen mass could dominate galaxies and clusters, a deeper question came into view. If invisible matter shapes the motions of stars and the binding of clusters, then it must also have influenced the large-scale growth of the universe itself. The hidden weight inferred from galactic and cluster dynamics could not remain a merely local mystery. It had to be placed inside a broader cosmic history, one that connected the present structure of the universe to its earliest detectable traces. To follow that connection, astronomy would have to listen not to the motion of galaxies alone, but to a much fainter signal spread across the sky, a relic glow that seemed to come from the beginning itself. As the hidden weight of the universe began to look less like a local irregularity and more like a structural fact, astronomy was drawn toward a deeper question. If unseen mass had helped shape galaxies and clusters, then the history of the universe could not be reconstructed from stars and galaxies alone. Those luminous systems were late arrivals. To understand how large-scale structure emerged, scientists had to look for evidence from a much earlier epoch, from a time before galaxies had taken shape, before clusters had formed, before the cosmos had settled into the pattern visible through telescopes. That search led not to a new object in the sky, but to something far more diffuse and unsettling, a faint radiation filling all of space, coming from every direction, so uniform at first glance that it seemed almost like a background flaw in measurement. NASA's overview of the COBE mission describes this radiation as a relic of the early universe, a surviving echo of the original hot fireball. The story of how it was predicted, discovered, and interpreted would transform cosmology from a largely speculative field into one increasingly tied to precise physical evidence. Long before that radiation was actually measured, the idea of a hot early universe had already begun to gather conceptual strength. In the 1940s, George Gamow, working with Ralph Alpher and Robert Herman, was trying to understand how the chemical elements could emerge in the early cosmos. Their reasoning led toward a universe that must once have been much hotter and denser than it is now. And from that picture came a remarkable implication. If the universe had begun in such a hot state and then expanded, the radiation present in that early epoch would not simply vanish. It would cool, stretch to longer wavelengths, and remain as a diluted bath of relic light filling all of space. NASA's COBE history notes that Alpher and Herman explicitly showed that a hot origin implied a faint residual background radiation still present in the modern universe. Later historical work has emphasized that Alpher and Herman's 1948 prediction deserves particular recognition, because in popular memory, the credit often drifted more broadly toward Gamow alone. This is a familiar pattern in the history of science. Ideas that later become central often begin quietly, attached to problems that only a small community is following closely at the time. At first, however, that prediction did not immediately reorganize cosmology. The field in the mid-20th century still contained competing large-scale visions of the universe, and not all of them demanded a thermal relic from an early hot phase. The steady-state model, associated especially with Fred Hoyle, Herman Bondi, and Thomas Gold, offered a very different picture in which the universe expands but maintains the same average appearance over time through the continual creation of new matter. In such a framework, the cosmos has no singular thermal beginning of the sort imagined by hot Big Bang models. Nobel background material on cosmology notes that the later discovery of the cosmic microwave background became one of the strongest blows against the steady-state picture. But before that discovery, the matter was not settled. Cosmology in the 1950s was not yet the highly constrained science it would later become. It was still possible for broad, elegant world models to coexist for years, supported by different theoretical tastes and limited evidence. That is part of what makes the eventual discovery so compelling. It did not come from a grand effort explicitly designed to confirm the early universe in one decisive gesture. It came from an antenna and a persistent excess noise. In 1964, Arno Penzias and Robert Wilson were using the Bell Telephone Laboratory's Horn antenna in Holmdel, New Jersey, for radio measurements when they encountered an unexplained background signal. NASA's COBE account describes it as an unexplained noise coming from all directions with roughly equal intensity. The signal did not vary in the way one would expect from an ordinary local source. It was not obviously tied to the city, the weather, the time of day, or a particular region of the sky. Penzias and Wilson did what careful experimental scientists generally do before embracing any large conclusion. They treated it as a technical problem. They investigated the instrument, considered possible terrestrial contamination, and even cleaned out the nesting pigeons and droppings that had accumulated in the antenna. Because in real scientific life, the road to cosmology sometimes passes through very mundane maintenance. The beauty of this moment lies in its mismatch between scale and significance. The early universe did not first present itself as a grand visual spectacle. It arrived as stubborn interference. Penzias and Wilson were not setting out to discover the thermal afterglow of the cosmos. They were trying to remove noise from a sensitive microwave system. Yet at nearly the same time, a group at Princeton led by Robert Dickey, with Jim Peebles, David Wilkinson, and Peter Roll, was thinking seriously about relic radiation from a hot early universe and preparing experiments to look for it. The broad historical outline is well known. When the Bell Labs team learned of the Princeton group's theoretical expectations, the unexplained signal suddenly acquired cosmological meaning. The universe, it seemed, was not merely full of galaxies and clusters. It was immersed in a faint microwave glow left over from a time when matter and radiation had once existed in a far hotter, denser state. This was one of the most consequential reinterpretations in 20th century science. Nothing in the instrument had changed, but the world described by the instrument had become much deeper. What made the signal so powerful was not only that it existed, but that it possessed the right character. It appeared nearly isotropic, almost the same in every direction, which is exactly what one would expect from a relic background pervading the entire cosmos, rather than from ordinary astrophysical sources concentrated in particular regions. Over time, that radiation would come to be called the cosmic microwave background, or CMB. Britannica describes it as the electromagnetic afterglow of the early universe, shifted by cosmic expansion into the microwave part of the spectrum. Nobel materials likewise frame it as decisive evidence for the hot Big Bang picture. The discovery did not answer every cosmological question at once, but it changed the basis on which those questions were asked. A universe with a measurable relic background was no longer just a matter of speculative cosmological geometry. It had a thermal history that could be probed. The cosmos had left behind a fossil record in radiation. The effect on the rivalry between cosmological models was profound. Steady-state theory had appealed to many because of its conceptual economy and its resistance to a singular origin event. But a near-uniform thermal background was much more naturally explained if the universe had passed through an earlier hot, dense phase. Nobel background documents on cosmology note that after the CMB discovery, many steady-state proponents abandoned the model, though not all did so immediately. That historical nuance matters. Scientific worldviews do not vanish in a single day simply because a new datum appears. People reinterpret, resist, refine, and argue, yet the balance had shifted. The CMB did not merely support the hot Big Bang. It made the universe look like something that had genuinely evolved from a radically different early condition. For the first time, cosmology possessed a pervasive, measurable remnant of its own beginning. Even then, however, the background was at first more of a cosmic fact than a detailed map. Astronomers knew it was there, and they knew roughly how hot it was. But to turn cosmology into a precision, science required much more. It was not enough to say that the universe glowed faintly in microwaves. Scientists needed to know whether that radiation had the exact blackbody form expected from a thermal origin, and whether it contained tiny anisotropies, minute differences from one direction to another, that could later grow into galaxies and large-scale structure. This raised a difficult observational challenge. The background is extraordinarily smooth, and its variations are tiny. Measuring them meant going beyond the initial discovery toward instruments of far greater sensitivity and stability. NASA's COBE history and the 2006 Nobel materials both emphasize that this next step was crucial. It is one thing to discover an echo. It is another to read information from the fine structure of that echo. The COBE satellite, launched by NASA in 1989, was built to do exactly that. John Mather and George Smoot, later awarded the Nobel Prize in Physics in 2006, were central figures in this phase. COBE addressed two questions that sat at the heart of modern cosmology. First, Did the CMB possess the near-perfect blackbody spectrum expected if it truly came from an early thermal phase of the universe? Second, was the background perfectly uniform? Or did it contain the tiny variations needed to seed later cosmic structure? Nobel Prize. Org states that Mather and Smoot were recognized for the discovery of the blackbody form and anisotropy of the CMB. And NASA describes these as among COBE's top achievements. The answers mattered because they connected the earliest observable radiation to everything that came later. A perfect thermal spectrum would confirm the universe's hot beginning with extraordinary precision. Tiny anisotropies would explain how a nearly uniform early cosmos could eventually become lumpy enough to contain galaxies, clusters, and the web-like architecture of the visible universe. COBE's results were among the great moments of 20th century observational science because they gave form to something almost paradoxical. On the one hand, the universe was astonishingly smooth at early times. On the other hand, it was not perfectly smooth. NASA notes that COBE measured the blackbody spectrum of the CMB and later detected the anisotropies, those tiny temperature variations across the sky. Nobel Materials stressed that these findings helped turn cosmology into a precise science. The blackbody result told physicists that the early universe had indeed been in an extraordinarily uniform thermal state. The anisotropy map told them that this uniformity contained slight departures, minute wrinkles in the density and temperature field, from which later structures could grow. This combination is conceptually beautiful. The cosmos began not as chaos, but as near order with a trace of asymmetry. Without that trace, there would be no galaxies, no stars, no planets, no biological observers, and no one to measure the relic light at all. To grasp why those anisotropies mattered, it helps to picture the early universe not as a collection of finished objects, but as a hot plasma in which matter and radiation were tightly coupled. Tiny fluctuations in density would alter the local temperature and pressure conditions, leaving faint imprints in the CMB when radiation finally decoupled and began traveling relatively freely through space. These fluctuations were extremely small, but gravity could amplify them over cosmic time, drawing matter into denser regions and eventually helping to build the large-scale structures astronomers now observe. In that sense, the CMB is not only relic light, it is a snapshot of the universe before galaxies, showing the primordial pattern from which later structure emerged. NASA's WMAP overview makes this logic explicit by describing how detailed maps of the microwave background reveal the seeds of galaxies and cosmic structure. The background is therefore both memory and blueprint. It preserves the past while foreshadowing the future. After COBE, the next great stage of the story involved refining that blueprint. If COBE showed that the anisotropies existed, later missions could resolve them with greater precision and on smaller angular scales. NASA's WMAP materials explain that the Wilkinson Microwave Anisotropy Probe produced much more detailed full-sky maps of the CMB, allowing cosmologists to extract quantitative information about the age, composition, and geometry of the universe with far greater confidence. This is where cosmology began to feel less like a grand narrative stitched together from a few dramatic facts, and more like an empirical science in the modern high-precision sense. The small ripples in relic radiation could be decomposed, measured, and compared with theoretical models. A universe once known only by philosophical speculation and the broad logic of expansion was now being read through tiny fluctuations in microwave temperature spread across the sky. It is difficult to think of a clearer example of science learning to draw deep reality from delicate traces. There is also a psychological subtlety in the history of the CMB that deserves attention. The early universe was not discovered through a dramatic visual event in the ordinary human sense. It was inferred from instruments, calibrations, radiometers, temperature scales, and statistical maps. This means that the emotional force of the story lies not in spectacle, but in interpretation. A persistent hiss becomes a relic fireball. A nearly uniform glow becomes a snapshot of the infant cosmos. Tiny anisotropies become the seeds of everything that later condensed into visible structure. That chain of reasoning is one of the finest examples of how scientific imagination works when disciplined by evidence. Scientists did not invent a dramatic picture and then go looking for supporting signs. They found faint, stubborn signs and slowly realized how dramatic a picture those signs required. The most astonishing part of the universe often enters human understanding through the most modest-looking data. And this is why the cosmic microwave background belongs so centrally in the story of invisible structures. It is not merely another discovery added to a growing list of invisible cosmic ingredients. It changes the temporal scale of the whole documentary. Gravity, fields, and dark matter show that much of the universe's structure is hidden in the present. The CMB shows that the present itself carries a barely perceptible memory of an early state from which all later structure emerged. The invisible is no longer only what surrounds visible objects or outweighs them. It is also what remains from a time before the visible universe, as we normally understand it, had fully formed. Relic radiation is not a thing among things. It is a background condition of cosmic history still washing across the sky. And once cosmologists learned to treat that background as data rather than noise, a larger possibility came into view. If the tiny variations in the microwave background were the seeds of later cosmic architecture, then the hidden mass already inferred from galaxies and clusters must have helped shape how those seeds grew. To follow that process, science would have to trace how invisible matter and faint primordial irregularities together assembled the vast structure of the universe on the largest scales. As the microwave background revealed the universe in its youth, it also posed a quiet but demanding challenge. The early cosmos looked almost smooth, and yet the later cosmos was anything but smooth. Galaxies gathered into clusters, clusters linked into larger associations, and between them stretched enormous regions of comparative emptiness. The sky, when viewed casually, can make the universe seem like a scattered display of isolated lights. But once redshifts, distances, and large surveys entered the picture, astronomers began to see that galaxies were not sprinkled randomly through space. They were arranged in patterns, and those patterns hinted that the growth of structure had followed hidden lines of organization for billions of years. The problem, then, was not simply how the universe began, but how a nearly uniform beginning became an intricately uneven cosmos without losing the memory of its early conditions. At first, this was a problem of both imagination and data. Before the era of large digital sky surveys, astronomers could identify clusters, note superclusters, and suspect that voids and filaments existed. But the full geometry of cosmic structure remained difficult to grasp. One needed not only telescopes, but systematic mapping across great volumes of space. The old method of looking at the sky object by object was no longer enough. To understand structure on these scales, astronomers had to think statistically and spatially at once. They had to turn galaxies into tracers of a larger pattern, and then ask what kind of underlying physics could produce such a pattern from the tiny fluctuations seen in the cosmic microwave background. This raised a new question, one that connected the whole documentary up to this point. If the universe is shaped by invisible structures, what does that hidden order look like when it is traced across hundreds of millions of light years? By the late 20th century, theorists had begun to describe the answer in a form that was both mathematically serious and visually striking. In 1996, Richard Bond, Lev Kaufman, and Dmitry Pogosyan published a landmark Nature paper titled "How Filaments of Galaxies Are Woven into the Cosmic Web." That phrase endured because it gave a name to something that simulations and theory were increasingly making plausible: large-scale structure. They argued, grows through gravitational instability from small initial fluctuations, producing a universe of clusters, filaments, sheets, and voids rather than one filled uniformly with galaxies. This was not just a picturesque metaphor. It was an attempt to describe the deep architecture of cosmic growth. Matter did not simply clump in isolated blobs. It flowed, stretched, and accumulated along a network-like pattern, shaped by gravity acting over immense expanses of time. The logic behind that picture emerged gradually from a combination of cosmological theory and numerical simulation. If the early universe contained small overdensities, then gravity would slowly amplify them. Regions slightly denser than average would draw in more matter, becoming denser still, while underdense regions would empty out relative to their surroundings. But because the initial fluctuations were not arranged as perfect spheres, collapse would not occur symmetrically. Matter would tend to fall first into sheets, then into filaments, and finally toward denser nodes where clusters could form. Over time, this produced a kind of cosmic skeleton. The densest intersections became the homes of rich galaxy clusters, while long filaments linked them across space, and vast voids opened between. The importance of the bond, Kaufman and Pogosyan formulation, was that it made this pattern feel like an outcome of ordinary gravitational physics working on extraordinary scales, rather than a decorative accident of the galaxy distribution. This picture also gave dark matter a far more expansive role than it had in earlier parts of the story. Dark matter was no longer just the hidden mass required to explain why galaxies rotate too quickly or clusters hold together too strongly. It became the scaffolding within which visible matter could gather. Because dark matter interacts gravitationally and appears to dominate the mass budget of cosmic structure, it could begin clumping earlier and more efficiently than ordinary baryonic matter, which in the young universe was more tightly coupled to radiation. As a result, the invisible halos and filaments of dark matter would help guide where gas later fell, cooled, and formed galaxies. In this view, much of what becomes visible in astronomy is really a late illumination of a structure whose deeper frame was already laid down invisibly. This changed the emotional feel of the cosmos. Galaxies began to look less like the primary substance of the universe and more like lit tracers along a darker, larger architecture. Yet theory alone, however elegant, was never going to be enough. The cosmic web had to be mapped, or at least strongly inferred, from observation. That is where the Sloan Digital Sky Survey became so important. SDSS's official science pages state that the survey has spent more than 20 years making maps of the universe, and that its data enabled sweeping three-dimensional views of large-scale structure. Earlier, NASA visualizations described SDSS as one of the most ambitious astronomical surveys ever undertaken. producing a 3D map of about 1 million galaxies and quasars. These maps mattered because they turned a conceptual picture into something much closer to a seen reality. As redshift surveys accumulated, astronomers could watch the galaxy distribution resolve into walls, filaments, knots, and open voids, the universe. When graphed in 3 dimensions, no longer resembled a random mist of points. It looked organized. There is a particular intellectual satisfaction in that transition from statistical suspicion to mapped structure. In earlier stages of the story, the invisible revealed itself through anomalies, through motions too fast, masses too large, or signals too uniform. Here, the hidden order becomes legible as shape. The Sloan maps did not directly show dark matter itself, but they showed the luminous distribution that theory predicted should trace the deeper gravitational framework. You could fly through the data and see chains of galaxies extending across space, broad cavities where few galaxies appeared, and dense intersections suggestive of the nodes where gravity had drawn matter together over cosmic time. The visual effect was powerful, but it was also scientifically disciplined. The web was not a fantasy imposed after the fact. It was the observed large-scale pattern emerging from one of the most systematic surveys ever undertaken. Even so, a galaxy map is not the same thing as a full map of matter. Galaxies are luminous signposts, but they are biased tracers, and much of the baryonic material between them can remain faint or difficult to detect. This led astronomers to a further challenge. If the cosmic web was real, then the gas in intergalactic filaments ought, at least under some conditions, to be observable more directly. For many years, this remained difficult. Simulations suggested that a significant fraction of ordinary matter should reside in diffuse filamentary structures between galaxies. But seeing that material was another matter. Filaments are tenuous, dim, and often overwhelmed by brighter objects. The large-scale structure of the universe could be inferred from galaxies and from theory, yet directly imaging parts of the web itself remained elusive. The architecture was convincing, but the substance filling its faint corridors was harder to catch in the act. A notable step came in 2014, when Nature reported what it described as the first direct imaging of a long-sought gas filament in the cosmic web. The observation, associated with a luminous quasar illuminating surrounding gas, allowed astronomers to detect extended Lyman alpha emission from a filamentary structure. Max Planck Institute for Astronomy and Max Planck Society releases on the same result explained the underlying idea clearly. The intense radiation from a quasar could act almost like a flashlight, causing otherwise faint intergalactic gas to glow. That did not mean the whole cosmic web had suddenly become visible in ordinary fashion, but it did mark a symbolic and observational advance. A structure long anticipated by simulations and indirect evidence had begun to step into partial view. The hidden architecture of the universe was not only being mapped through galaxies and statistics. In special circumstances, parts of its intergalactic substance could be made to shine. This was a beautiful continuation of an older pattern in the history of physics and astronomy. The unseen is first proposed because it explains an otherwise stubborn discrepancy. Then it is supported by simulation, by structure in the data, by multiple converging lines of evidence. Only later, and often only partially, does it become possible to image or isolate some portion of what had long been inferred. The cosmic web followed that rhythm closely. First came the theoretical picture of structure growth from primordial fluctuations. Then came redshift surveys showing galaxies arranged in web-like form. Then came more direct glimpses of gaseous filaments under favorable conditions. At each stage, the universe became more legible without becoming simpler. The web did not reduce the cosmos to neat geometry. It revealed a world in which order emerges from long gravitational evolution, where the visible gathers along pathways laid down by invisible mass and early fluctuations. As observational cosmology continued to improve, the cosmic web also became central to broader questions about dark matter and dark energy. ESA's recent Euclid materials describe filaments of ordinary matter and dark matter weaving through the cosmos, and emphasize that understanding this structure is essential for grasping the nature of the universe's dominant components. Euclid imagery and science releases present the web not merely as a static pattern to be admired, but as a laboratory for testing cosmological models, the way galaxies cluster, the way filaments connect nodes, the way dark matter can be inferred from lensing and large-scale structure, all provide clues to the rules under which the universe grows. In this sense, the cosmic web is not just the product of earlier invisible structures. It is an active diagnostic of them. By reading its form, scientists hope to learn how much dark matter there is, how it behaves, and how cosmic expansion has influenced the growth of structure over time. There is something almost biological in the language that cosmologists sometimes use for this architecture, and it is worth pausing over why that language persists. A web suggests connection, tension, and transmission. It suggests that the whole cannot be reduced to isolated points. That turns out to be exactly the right emotional register for large-scale structure. Galaxies are not only individual systems. They belong to environments, corridors, inflows, and nodes. Matter streams along preferred directions. Clusters form at intersections. Voids widen as material drains away from them. The universe, in other words, behaves less like a pile of separate islands and more like a connected, evolving network. The term cosmic web endures because it captures this relational truth without pretending that the underlying physics is mysterious in a mystical sense. The web is not a metaphor for magic. It is a metaphor for gravity, dark matter, and time working together on the largest scales accessible to observation. By the time this picture had fully entered mainstream cosmology, the cumulative lesson of the documentary had deepened once again. Newton had shown that invisible order could govern motion. Faraday and Maxwell had given structure to the space between objects. Einstein had made geometry itself dynamic. Dark matter had revealed that much of the universe's mass is not luminous. The cosmic web brought those lines together into a single visual and conceptual architecture. It showed how tiny irregularities in the early universe, amplified by gravity and shaped by hidden mass, could grow into the largest structures ever mapped. The present universe was not simply cluttered with galaxies. It had a skeleton, a growth pattern, and a memory of its beginning written into its structure. Yet even here, where the invisible had become grandly architectural, the story was not complete. The web and the matter within it described how structure formed and held together. But they did not answer every question about why the universe behaves as it does on the largest scales. For that, the narrative must turn one final time toward deeper ingredients that seem to shape reality while remaining stubbornly out of sight. As the architecture of the cosmic web came into view, the universe seemed at once more intelligible and more elusive. The large-scale pattern of galaxies could now be described as the visible expression of much deeper processes, shaped by primordial fluctuations, dark matter, and the long, slow work of gravity. Yet the very success of that picture exposed a final and disquieting truth. even after centuries of progress, even after fields, space-time curvature, hidden mass, and relic radiation had entered the language of science. Much of the cosmos still rested on foundations that were described more confidently than they were understood. The great narrative of invisible structure had not ended in clarity of substance. It had ended in a more refined form of uncertainty. The universe held together, evolved, and revealed itself through patterns that human beings could increasingly map. But beneath those patterns were ingredients and principles whose nature remained partly veiled. If the earlier sections of this story taught science how to accept the unseen, the final section shows how far that acceptance has had to go. One of the most striking examples lies not in the scale of galaxies, but in the intimate grammar of matter itself. During the middle of the 20th century, particle physics was beginning to discover a new kind of problem. The elementary particles described by emerging quantum field theories did not fit comfortably together if one simply assigned masses to them in the most direct way. Certain symmetries, especially those needed to make gauge theories mathematically consistent and predictive, seemed to resist straightforward mass terms. Yet the world plainly contained massive particles, the carriers of the weak force, later known as the W and Z bosons, could not behave as massless entities, and fermions too possessed mass in ways that demanded explanation. This was not merely a bookkeeping issue. It was a structural tension at the heart of modern physics. The equations worked best when they preserved elegant symmetries, but the visible properties of nature seemed to require those symmetries to be hidden, broken, or transformed in some subtler way. Out of that tension emerged one of the most important conceptual shifts in 20th century physics. In 1964, several physicists working independently, including Peter Higgs, François Englert, Robert Brout, Gerald Guralnick, Carl Hagen, and Tom Kibble, proposed related mechanisms through which gauge symmetries could remain fundamental, while particles nonetheless acquired mass through interaction with a pervasive field. The key idea was delicate but profound. Space would not be empty in the deepest quantum sense. Instead, it would possess a non-zero field value even in what we ordinarily call vacuum. Particles moving through that background would interact with it differently, and those interactions would appear as mass. Here again, the visible property of an object turned out to be inseparable from an invisible structure extending through all of space. Mass was no longer simply something matter carried in isolation. It became, at least in this framework, partly relational, arising from how particles moved through an unseen field that filled the universe. Peter Higgs himself was not cast in the dramatic mold that popular science stories sometimes prefer. Nobel biographical material presents him as a reserved and thoughtful figure, shaped in part by childhood illness and long habits of quiet study. There is something appropriate about that, because the Higgs field entered physics not as a spectacular event in nature, but as a disciplined theoretical response to a problem of internal consistency. It was a proposal born from abstraction, symmetry, and necessity rather than from an obvious new phenomenon visible in a telescope or laboratory photograph. This makes it especially fitting for a documentary about invisible structures. The field was real. If it was real at all, not because anyone had seen it directly, but because a deeper theoretical order seemed to require something like it. The mind had once again moved beyond visible surfaces toward a substrate inferred from the logic of the world. For decades, however, that logic remained incomplete without experimental support. The Higgs mechanism solved a conceptual problem, but a theory of this kind cannot live forever on elegance alone. It had to leave some trace that could, at least in principle, be detected. The associated particle, the Higgs boson, became the most famous of those traces. Yet detecting it required energies and instruments far beyond what physics possessed in the 1960s or 1970s. This long interval between proposal and confirmation is one of the quietest and most revealing chapters in modern science. A generation of physicists learned to treat the Higgs field as an indispensable part of the Standard Model, while still waiting for the empirical sign that would justify that confidence fully. It was another example of a recurring pattern. Structure is inferred first. Detection comes later, sometimes much later, and sometimes only through one fleeting consequence of the deeper reality one is trying to describe. The Large Hadron Collider at CERN became the machine through which that waiting was finally addressed. Built on a scale that reflected the maturity of modern high-energy physics, it accelerated protons to enormous energies and brought them into collision so that rare processes could briefly appear in the debris. In July 2012, CERN announced the observation of a new boson consistent with the Higgs particle. And in 2013, the Nobel Prize in Physics was awarded to François Englert and Peter Higgs for the theoretical discovery of the mechanism that contributes to our understanding of the origin of mass of subatomic particles. What mattered here was not simply the detection of one more particle. It was the experimental confirmation that the vacuum itself is structured in a way that affects the properties of matter. A field permeating all of space, ordinarily invisible and inaccessible to direct experience, had become part of the established explanation of why the world's basic constituents possess the masses they do. The old image of emptiness had receded once again. Even so, the Higgs field did not close the story of matter and mass. It clarified one part of the Standard Model, but it did not explain dark matter, and it did not by itself answer why the values of the masses are what they are. The deeper lesson was more philosophical than final. Matter had become inseparable from vacuum structure. What appears solid and intrinsic at the everyday scale turned out, under deeper scrutiny, to depend on background fields that never announce themselves directly to the senses. The visible world continued to rest on invisible order. And as particle physics reached this strange and elegant conclusion, cosmology was moving toward another surprise, one that seemed to concern not the contents of the universe alone, but the behavior of expansion itself. The return of the cosmological constant is one of the most beautiful ironies in the history of science. Einstein had introduced that term in 1917 in order to maintain a static universe, then later abandoned it when cosmic expansion became the more natural picture. For much of the 20th century, the cosmological constant lingered at the edges of cosmological discussion, sometimes useful, sometimes suspect, often treated as an adjustable term rather than a compelling physical necessity. Yet by the late 1990s, observations of distant Type 1a supernovae began to suggest something startling. The universe was not merely expanding. Its expansion was accelerating. The Supernova Cosmology Project and the High Z Supernova Search Team, working independently, found that distant exploding stars appeared dimmer than expected in a decelerating universe. The implication was not immediately obvious in emotional terms, but physically it was extraordinary. The large-scale behavior of space-time seemed to be driven by something that acted against the slowing pull of gravity. This raised a new question that was both old and new at once. What sort of thing can make the expansion of the universe speed up over time? The answer is still not known in a final sense, but the observational inference became central to modern cosmology. A component now called dark energy, or in some formulations, a cosmological constant associated with vacuum energy, entered the model of the universe. The name itself tells part of the story. As with dark matter, the term does not mean that science has grasped the underlying substance clearly. It means that there is an effect, coherent across multiple observations, that seems to require a component or property not accounted for by ordinary matter and radiation alone. The late 20th century therefore added another invisible structure to the cosmos, not because scientists wanted more mystery, but because the large-scale behavior of the universe forced the issue. The expansion history would not fit the simpler picture. What makes dark energy especially unsettling is that it reverses the emotional direction of gravity. So much of the history of cosmic structure concerns gathering, binding, and collapse. Gravity pulls matter together, builds stars, shapes galaxies, and deepens the nodes of the cosmic web. Dark energy, by contrast, belongs to the story of separation. It becomes dynamically important on vast scales and over long times, altering the future of the universe not by creating local structure, but by influencing the geometry of expansion itself. In this sense, it feels almost like a counterpoint to the rest of the documentary. Earlier invisible structures made the world coherent by connecting and binding. This one seems to govern dispersal, the stretching of the cosmic stage beyond what matter alone would dictate. Yet it belongs to the same family of discoveries. Once again, a hidden component is inferred because the visible universe refuses to evolve as expected under older assumptions. There is a temptation, when speaking of dark energy, to make the mystery sound larger than it needs to be. In truth, its scientific power lies in its restraint. Cosmologists do not claim to have seen dark energy as one sees a nebula or a detector trace. They infer it from the expansion history of the universe, from supernova observations and other cosmological measurements that together support an accelerating cosmos. What the term provides is not a final picture, but a provisional and mathematically useful way of naming a profound gap between expectation and observation. In that respect, dark energy resembles some of the earliest invisible structures in this documentary. Newton could describe gravity before its deeper mode of action was understood. Zwicky and Rubin could infer dark matter before its microscopic identity was known. Now, cosmology describes an accelerating universe before it knows whether the cause is truly vacuum energy, a cosmological constant, a dynamical field, or some deeper revision to gravity on the largest scales. The universe continues to ask science for patience. And then, in a strange and beautiful way, another chapter of Einstein's theory returned from the future to meet the present. General relativity had long implied the existence of gravitational waves, ripples in space-time produced by accelerating masses. But for most of the 20th century, they remained an almost ghostly consequence of the equations. They were accepted in principle by many physicists, yet difficult to imagine ever being detected directly, because the distortions they produce are astonishingly small. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was built to pursue exactly this almost impossible measurement. Its scale and precision reflect a mature scientific culture, willing to spend decades building instruments to detect effects that common sense would consider inaccessible. In September 2015, LIGO observed the signal later designated GW 150914, produced by the merger of two black holes more than 1 billion light-years away. When the result was announced in 2016, it marked the first direct detection of gravitational waves. The importance of that moment is easy to state and difficult to fully absorb. A century after general relativity was formulated, one of its most subtle predictions had become measurable. But beyond the triumph of confirmation, something deeper had happened. Space-time was no longer only a geometric framework inferred from planetary orbits and bent starlight. It had become, in a new and almost auditory sense, a dynamic medium whose ripples could be recorded as events. Scientists often speak of gravitational wave astronomy as opening a new window on the universe. And that phrase is accurate, though perhaps still too visual. In some respects, it opened a new way of listening. Black holes, invisible by definition in the ordinary optical sense, announced themselves by the trembling they induced in space-time itself. Once again, the unseen did not arrive as an image. It arrived as a pattern in exquisitely measured data, a disturbance read from a deeper background than the eye could ever access. This is where the strands of the documentary begin to gather into a final philosophical form. The Higgs field tells us that the vacuum of particle physics is structured. Dark energy tells us that the expansion of the universe may be governed by something not contained in visible matter at all. Gravitational waves tell us that space-time is not only geometric, but dynamically expressive. Each of these discoveries deepens the same lesson in a different register. Reality is not built only from objects, not even primarily from objects in the most naive sense. It is built from fields, geometries, hidden components, and background conditions that shape what objects can be, how they move, and how the universe evolves. The visible world is not false, but it is secondary. It is what invisible order looks like once it passes through matter. Light, motion, and time. There is also something deeply human in the way this understanding has been won. None of these structures announce themselves in forms naturally suited to the senses. They had to be inferred through equations. Instruments, anomalies, collisions, spectra, lensing maps, background radiation, and interferometric whispers. Scientific curiosity, in this long history, has been less like conquest than like training. It has taught human beings to trust indirect evidence, to refine the meanings of reality, and to live with truths that become clearer the less they resemble ordinary experience. That habit is one of the great achievements of the scientific mind. It is not simply the accumulation of facts. It is the disciplined widening of what thought is willing to admit as part of the world. And yet the widening is unfinished. Dark matter remains unidentified. Dark energy remains conceptually unresolved. The Higgs field, though confirmed in one vital respect, opens onto deeper questions about vacuum structure and naturalness. Gravitational wave astronomy has begun, but it has only begun. The universe still appears to rest on invisible foundations whose full meaning is beyond present reach. There is no shame in that incompletion. On the contrary, it may be the most faithful ending possible for a documentary like this one. To understand the cosmos is not to strip it of mystery, but to discover that mystery can become sharper, more exact, and more beautiful when approached through evidence. The search does not end when something is named. It changes form. It becomes more precise, and sometimes more profound. And somewhere beyond the visible brilliance of stars and galaxies, the hidden structures of the universe continue their silent work, holding together a reality that human beings have only begun to read. Tonight, we have followed a strange and beautiful idea to its edge. The universe is not held together only by what shines, or by what can be easily pictured in the mind, beneath the stars, behind the galaxies. And woven through the silence of space are structures that do not present themselves directly to the eye. Fields, curvature, hidden mass, relic light. And the deeper frameworks of modern physics have changed the meaning of reality itself. They have shown that nature is often most powerful where it is least visible, and that the deepest order of the cosmos may first appear not as an image, but as a discrepancy, a pattern, or a whisper in the data. That discovery has changed more than science. It has changed the habits of thought by which human beings approach the world. The scientific imagination learned, slowly and sometimes reluctantly, to accept that truth does not always arrive in a form the senses can immediately grasp. Sometimes it appears as an anomaly in the motion of galaxies, sometimes as a faint signal that refuses to disappear, sometimes as a mathematical symmetry so elegant that it suggests the world may be organized around it. In that sense, the history of invisible structures is also a history of intellectual humility. The universe has repeatedly asked us to believe that reality extends beyond appearance, and science has advanced by learning how to listen with increasing patience and care. And still, the search remains unfinished. Even now, much of the cosmos seems to rest on foundations we can describe more confidently than we can fully understand. Perhaps that is the most enduring lesson of all. Knowledge does not end when a mystery is named. It deepens. It becomes more precise, but also more profound. And as the visible universe settles once more into silence, the unseen continues its quiet work, shaping the world beyond our sight and inviting the next question.